All right, in the last video, we talked about all 5 of the different types of radioactive decay that happen, and we were going to talk about trying to put them in context. How does this actually occur? And then we're going to have to talk about whether things are stable, whether the nuclei are stable or not, whether things are going to emit radiation. It turns out that all elements with a Z value bigger than 82, what that means for us is, you're going along the periodic table. As soon as you hit 82, it's the last stable one. Anything above that, every single one of these with a number bigger than 82 is radioactive. Which means they're going to do one of those 5 types of radioactive decay. Most of them actually decay very slowly. And it does depend on the different isotope. So like uranium, there's uranium-235 and uranium-238. 238 has a half-life of like billions of years, but 235 is pretty reactive, immediately so, okay? And some of these things can be forced to undergo a radioactive decay. But here's an example of something called a radioactive decay series. It's a little random because most of these elements can emit more than one type of radiation, and it's kind of random as to which one it's going to do. But here's an example of something that is a radioactive decay series. So uranium-238 is a pretty common alpha particle emitter. It's the one we used as an example in the last video. Okay, so alpha particle emitter. So to make this balance out, that's an alpha particle. We need the numbers to work out, so this would be a 90, this would be a 234, and element 90 is thorium. Okay, we've seen that, not a big deal. But it turns out that thorium is also radioactive. This specific isotope is a pretty common beta particle emitter. It turns out that alpha and beta particles are the most likely targets on this. The other options are possible, but they're the most likely. So this thing will undergo a beta particle emission. And so for this to work, this would have to be a 91, which is element 91, which is protactinium. Some of these elements we'd never see otherwise. Okay. Turns out that protactinium is also a beta particle emitter. So same idea. And what we end up with is this is still a 234, but this is now a 92, which is back to uranium. And it turns out that uranium-234 is another isotope that's possible. It's also a pretty common alpha particle emitter. So on and so forth. Okay, and what we get is a 90, and this is now a 230. I can't do math apparently. But we have a thorium again. But it turns out this isotope of thorium, this one was a beta particle emitter. This one apparently is an alpha particle emitter. It's most likely to do that. So to make this work, this has to be an 88, and 230 minus 4 is 226. Element 88 is radium. And radium is an alpha particle emitter, and so on and so forth. And the idea is this would just continue and continue and continue until it'll bounce around, and sometimes you get heavier elements, lighter elements, whatever. It'll bounce around until you get to lead. Lead, it turns out, is super stable and not radioactive at all, which is why there's a bunch of it in the ground. Okay. So basically, this thing's kind of bouncing around like, I don't know if you guys ever seen The Price is Right, but there's a game called Plinko where it literally just bounces around, and sometimes it even bounces back up a little bit and bounces around, and then it hits the bottom. This is the bottom. You will never have a reaction where you start getting like radioactive decay that ends up somewhere down here. Okay, it's always these top guys, and then as soon as it hits 92, it's done. Okay? Some perspective on this. This makes it look like it happens in like 5 minutes. This process could literally take a million years. Okay, so there are half-lives for how long this works. And the longer, we talked about half-lives in the kinetics chapter a long time ago. And these are all first-order reactions, so there's kind of a constant half-life no matter how much there is. The longer the half-life, the more likely you are to find this stuff, the more abundant it's going to be. The shorter the half-life, the harder these things are going to be to find. They don't last for very long. So, for example, if you went out with a shovel somewhere on the planet, the odds of you finding uranium-238 is pretty high because its half-life is literally billions of years. But if you look at something like francium, its half-life is like, I want to say it's like 8 minutes. It's really, really, really unstable. So you could dig around for, you know, you have a team of 1 million people digging around for years, and the odds of you finding francium is slim to none. You probably wouldn't find it. But uranium, not too hard. Okay. Doesn't mean it's not radioactive, but yeah. Okay. Well, we have seen uranium as the starting thing quite a few times at this point. It turns out that anything that is above element 92 are called the transuranium elements. So lead is kind of the dividing factor between not radioactive and radioactive. Uranium is the dividing factor between radioactive but real and pretty much fictional man-made synthetic chemicals. Okay. It turns out that anything above element 92 you will not find in nature no matter what. Okay, if you went around with a shovel looking for, you know, berkelium, it literally is physically impossible that you would find this. Okay? We make it, so this is uranium, we make those elements by taking uranium and then bombarding it with neutrons or other things. We usually start with uranium-238 because it's super stable. We don't really want an explosion in this case. But we shoot things like neutrons because they have mass and it makes bigger elements. It makes things heavier. Sometimes we can also shoot other nuclei. Nuclei is the word for just the nucleus part of an atom. It's the plural of the word nucleus. Okay. So if you wanted, you know, plutonium, you can't go dig that up. You have to make it. It's made synthetically made in a lab. So what you would do is you take uranium-238 and you literally just shoot a neutron at it. I don't actually know how that process works. I don't know where they get a neutron from, but apparently it is physically possible. Okay. And in terms of changing the numbers, this is just a 92. Great. Okay. But this number has now gone up to a 239. Turns out that this thing is fairly unstable and it'll happily undergo a beta particle emission. So I'm gonna write a beta over here. And the beta particle is that, which means this will be a 93. This is Neptunium. You'll probably notice these were named after planets. Uranium, Uranus, Neptune, Pluto, uranium, Neptunium, plutonium. The names down here get a little stupid, like Americium, Californium, Berkelium, that's curium, Californium, Einsteinium, Fermium. Fermi was part of the Manhattan Project. Mendeleev made the periodic table. They started naming them after people. Nobelium, he's the guy who made Nobel Prizes. He also invented dynamite, whatever. Anyway. But the names here, anything after 92 is pretty much fictional. Well, it turns out that this thing is super unstable. And it'll also undergo a beta particle. And what we form now is this becomes 94. And this is 239, which is plutonium. Plutonium is unstable also, but it's way more stable than neptunium. We'll talk about stability here in a second. Okay. The problem is this process can only go so far. You can only make things so much heavier by keep emitting beta particles, because what's happening is these things, what you're doing is you're taking neutrons and converting them into protons. But you're not gaining any mass, and there's always this balance between the number of protons and the number of, like, the overall mass, the number of protons and the overall mass of the atom. If this number gets too high before this number if this number doesn't get high enough with it, the thing becomes unstable and it falls apart. So, there are some elements, like this periodic table doesn't even have it drawn, like element 114, we have made that. So let me write, can only go so far. So this isn't the only way to make this happen. To make element 114, literally what they've been doing is they've been taking plutonium 242, this number up here would be a 242, and they shoot a calcium nucleus at it, just the nucleus, which has a mass of 48. And what you end up with is something that has 114 protons. This is element 94, calcium is element 20. So basically the final result is 114 protons. Here's the problem though. This is stupidly unstable. Like, we have made it, I think maybe twice, and it has not existed for more than a microsecond. And we were just able to piece together later that we even formed it. So as far as I am concerned, anything past plutonium is so unstable that it's literally, absolutely, completely useless. And as far as I'm concerned, it's not even worth writing on the periodic table. We have made them, but they are absolutely useless. So, every once in a while you'll see on the news like, oh man, people got a particle accelerator somewhere and they made element 116, 117, 118. Anything above 94, this is like the last one that's stable enough that we could like store it for later. They're all literally worthless. I guess end rant. All right, let's talk about nuclear stability. So like, why are some of these things more stable than others? Well, here's the thing about that, is it's not as clear-cut as we have seen when we talk about electrical stability, electrons. So when we talk about stability of atoms based on their electrons, what we generally say is the noble gases are super stable, okay? One other way to phrase this would be anything that has 2, 10, 18, 36, 54, and 86 electrons is the most stable option available. It doesn't give you the gory details as to how it's more stable. It turns out it's full orbitals and such, but core electrons and all that. But it turns out that for nuclear stability, we don't really know how the nucleus is structured enough to be able to go into that level of detail, but we do know a little bit. It turns out, obviously there's only 92 real elements, but there are multiple isotopes for each one. Like tin in and of itself has 10 isotopes. So we're going to talk about isotopes in terms of just the nuclei by themselves. It turns out that there are about 160 stable nuclei, individual isotopes, that have an even number of protons. I'm going to use this for a number because I'm lazy. And an even number of neutrons. Okay? Even is apparently helpful. There are about 50 stable nuclei that have an even number of protons and an odd number of neutrons. Okay. It turns out that there's also about 50 stable nuclei that have an odd number of protons right, sorry. And an even number of neutrons. It turns out that there are only 4 stable nuclei that we've ever discovered, and we know quite a bit about this, that have both an odd number of protons and odd number of neutrons. So in other words, at a first glance, the main thing we can spot is that even numbers are better than odd for both individual things. Okay. Here's the problem, is that we don't know enough of the details to be able to tell you why certain isotopes are more stable than others. But here are some trends. So like I said earlier, one way to describe number of electrons that are stable, you know, the double gases, would be 2, 10, 18, 36, 54, and 86. Well, it turns out that we know the numbers for what the most stable nuclei are. We just don't know why they're stable. Okay. It's based on something called nuclear shell theory. The idea is that protons and neutrons have some sort of structure, like they're packed together, they're organized in different energy levels in the same way that electrons are. Okay. The beauty for you guys, I guess, in terms of not having to learn it, is that we don't actually know how it works. We just know that it's there. Okay. But we do know the numbers that work out best. And I'm not joking when I tell you that they are referred to as the magic numbers. I love when science gets desperate and they start calling things magic. These are the most stable options for numbers of protons and neutrons. So P and N for protons and neutrons. Okay, I do not need you to memorize these set of numbers. I'm just kind of pointing out a few things here. So it turns out that having 2, 8, 20, 28, 50, 82, and 126 are the best options available for either of those numbers. Seems kind of random, right? But so does 2, 10, 18, 36, 54, and 86 if you didn't know how orbitals worked. Okay? Let's look at a couple examples just to see how this works, and then we'll end this video, I guess. So that was page 7, I guess this is page 8. Okay, so example. It turns out one of the reasons alpha particles are the most likely thing to be shot out of a nucleus is because literally this is made of nothing but magic numbers. This has 2 protons and 2 neutrons. Both of those are magic numbers. I guess I'll leave this up here so I can refer to it a lot. They both have 2. That's a stable answer, so this exists. Okay. 10, which is element 50, which is one of the stable numbers, the magic numbers, has the most isotopes of any element on the periodic table. And the reason is the number of neutrons is going to be different for each isotope, but the number of protons, no matter what, one of the 2 numbers is going to be one of these happy normal numbers. Okay? The reason that the radioactive decay series ends with lead is because lead is really freaking stable. Okay? Lead is Z equals 82, which is also one of our magic numbers. I pointed at the wrong one, but it's one of the magic numbers. And it turns out that the most common isotope is lead 208. If I could write things in the right order. Lead 208, which is essentially the protons is equal to 82 and the neutrons is equal to 126. Okay. Both of those are magic numbers. So in other words, what happens is during those radioactive decay series, when we have things that are heavier than lead, they're all radioactive, and as they decay, they end up decaying into something less stable, or something unstable. until it hits lead. As soon as it hits lead, 208's the most likely option. If you hit this staple of a compound, it's not going to be radioactive anymore. So this isn't perfect, but anything that we can look at that has those magic numbers in it, as either as the number of protons or the number of neutrons, or both, is going to be inherently stable. One of the reasons that that calcium-48 was shot at a plutonium to make element 114 is that's 20 and 28. They're both really, really stable, which means the thing wasn't going to explode. Sometimes when you do nuclear chemistry, you need to worry about whether or not the whole thing is going to blow up. Okay, all right, thanks.